Hi, I'm Jim Larson, and this is a 3D printed Stirling engine. And this is it's a new design. My first attempt, I went through 5 iterations, finally got one to run, but I didn't think it was easy enough for everyone to make it work. So I've redesigned, and this is going to be my first attempt at running it. Now, I usually never film the first attempts because sometimes they don't go that smoothly. Sometimes they don't go at all. But just a little bit about the design of this engine. In the first engine, the displacer inside the pressure chamber was printed out of PLA, and that worked for a while until it got hot enough that it melted, and then things didn't work anymore. So now um, I've gone back to an old technique I used to use with Stirling engines years ago, and this is floral foam. It's the same stuff that florists use for making flower arrangements. It's tolerant of high temperatures, very easy to shape and to form and to work with. In fact, I've made a couple of tools that are included in the 3D file for cutting and trimming these things. So this is like a bore that will be used to bore through um, a block of floral foam and make that cylinder just exactly the right size. Or then I've also got the cookie cutter method. This worked really well too, so I'm going to include both of them in the final model. So an aluminum can is used, and I use the section of the can that's kind of universal in Europe and in the United States. I think it's 330 milliliter can in Europe, and it's a 12-ounce can in the United States. The only primary difference in the dimensions is that the European can is a little bit shorter. But it only uses 80 millimeters of the sidewall of the can for the longest section. And the sidewalls in Europe are 100, and in America, I think they're like 105. So you can cut that piece out, and I'll go through some details in the instructions and how to work with cutting up aluminum cans. It's quite an art form, and it can be fun. So the cold section up here on the top is going to be filled with this ice water to cool the top of the engine, and then the bottom is going to be exposed to a candle flame, which is one of the tricky bits about 3D printing a Stirling engine. So anything that's exposed to the candle flame has been covered with silicone or is made out of metal. So I used RTV silicone to attach this can at the bottom, and then I coated the bottom of the engine with the RTV silicone. And the top piece is glued in with epoxy because epoxy is much easier to work with. This silicone is a bit of a curse. Anything it touches, it immediately sticks to and stains. And it doesn't level out. It's going to stay in whatever shape you smooth it out into. So you can see my fingerprints all over it. And it's somewhat caustic, so I use rubber gloves when I'm working with that stuff. It's two separate can pieces, and that's intentional. In my first design, I used one can piece, but you get what's called a thermal leak when you do that. And what that means is the heat from the bottom of the engine just gets transmitted up through the sides of the aluminum can and melts all of your ice up here, and the engine doesn't run very long. So in this circumstance, I've used two cans, and it's got that silicone, RTV silicone, as a thermal insulator between the cold side and the hot side. The drive diaphragm is made of a rubber balloon, and I've made some pieces that just snap together so that you don't have to glue on the balloon. You just take the little plug and snap it into the hole on the end of the shaft, and that holds the balloon. And then it's got a compression ring to keep things sealed there. It's just a 12-inch party balloon. And then in setting up the engine, it's set up like a standard Stirling engine in that there's a 90-degree offset between the drive side and the displacer side. So when this displacer crankshaft is down, this one is over at 90 degrees. You can see that one is kind of over to the side. that one is straight down. And then because I've always designed Stirling engines with adjustability in them, so they're easier to assemble and get things right. So there is one screw that you have to buy. If you don't have access to the screw or anything, you can just glue this piece once you get it in the right spot. But I like the screw simply because if I get it in the wrong spot, I can change it. The rods are made of 1.5 millimeter carbon rod, which is real common in model making. So model airplanes, model cars, model boats use this stuff as a push rod. And I got mine off Amazon. I think I got, well, you get a whole package of them for about $5, and it takes less than one rod to make the engine. So that's the fundamentals. Let's see if I can get some ice in here. One of the problems I made with the first one was there was not enough room to get ice cubes in it. So that's why I've made this kind of off center. My ice all froze together. Okay, so I've got some cold water. Should get that up as high as I can. Okay. I've also hot rodded a tea light candle by poking 2 more holes and pulling the wicks out of 2 other candles. So now I have a 3-wick candle. So my previous engine ran best if it was sitting over 3 candles. So now we've got 3 in 1. All right, candles are lit. Now we're waiting for the air inside to start to warm. Shouldn't take too long. Looks like we got it on the first try. So there it is, first running. Some of the things to watch for when you're setting it up: the drive diaphragm over here should not have to stretch the balloon, but you also don't want excess slack in it. So you need to adjust the tension on it so it can move up and down without causing it to stretch or without losing pressure to the motion of the slack balloon. One of the things that we can adjust here is the position of this drive shaft up here. That controls the length of the throw. Going to run a little faster there with a longer throw. It ran real quick there briefly because the air in the bottom was heating up without any cooling going on. Let me try and see how it does on the short throw. So this is like having your engine shifting into high gear before you should. So it's kind of lugging it down a little bit. It seemed to run pretty good out there with the longer throw. I'm going to let this go for a little while so that I can see if the PLA plastic on the bottom is going to survive. And feel it down here to see how hot it's getting. Bottom side's a little warm, but I don't think it's dangerous. In a worst case scenario, if it melts through, the water will leak out and put out the fire. I publish my 3D models on MakerWorld. I'm Jim Larson, and I'll put a link in the description for the video where you can find this 3D model once it's finally finished and published. Now that I have it operating and I'm pretty happy with the way it's working, my next step is to write some detailed instructions for how to build it, how to cut the aluminum, what some of the specific measurements are for the carbon shafts, and I think it's a good project. It's turned out really well. It does what it was designed to do. Thanks for watching.